All right, let's take a look at the cross example problem, Unit B for page 8. This is a big hunk of concrete used as a hydraulic dam. So let's take a look at this problem statement. Dams can vary from very large structures with curved faces holding back water to great depths, as shown in the video. A good example is maybe Hoover Dam. That's a curved structure, of course. Now, this is a relatively small structure with the praying faces. Here's the praying face of this concrete. And this is the concrete. Okay, so let's assume that the concrete dam has a weight. Actually, this is not the weight. This is a weight per unit volume. This is specific weight. So specific weight, 23.6 kilonewton per cubic meters. This is how heavy this concrete is per given volume. Okay. This is resting on a solid foundation. Okay. Let's determine the minimum coefficient of friction between this one and solid foundation, which is here. Coefficient friction. Minimum coefficient friction required to keep this dam from sliding at the water depths 4 meters here. In other words, if the water depth gets higher and higher and higher, it is going to develop larger and larger value of hydrostatic resultant force that actually trying to slide off this concrete block. Okay. So in order to prevent that, how much static friction coefficient do you need between this concrete dam and this solid foundation? Okay. You don't need to consider possible uplift along the base. That means, do you think this concrete dam beginning to kind of uplift from the bottom and then tip over? No, it's not going to happen. It's not going to happen. It's quite important. So anyway, the problem statement says you do not need to consider possible uplift along the base. I guess you have to ask question why. Why is that? Well, anyway. So base your analysis also on the unit lengths of this concrete dam. Unit lengths, what do you mean by that? So important two terms. So let's take a look at. So this is merely cross-section of this concrete structure, cross-section. It's not the cross, it's not just a whole picture. So in reality, this concrete probably looks like this. It just extends with certain widths, okay? This is probably in reality. Now the problem is saying, let's base your analysis for unit lengths of the dam. What is the unit length? Unit length really is, you are going to choose 1 unit of length. In this case, 1 meter. So this is 1 meter length of this very, very, very long concrete structure. So you're going to cut out this much amount of concrete. And then for this much amount of concrete, how much friction do you need? You're going to analyze that. So this is called quasi-two-dimensional analysis, Q2D analysis. So this really means that this really is a three-dimensional analysis, but we are going to based on unit widths of 3D object. This is called quasi-two-dimensional analysis, Q2D. Okay? So as you can see, I'm going to cut out unit lengths of this concrete. And then find out how much static friction coefficient we need. Okay. So what is the first thing? First thing is, let's define the coordinate system. So this is where this is a plane surface meet up with zero gauge pressure line. So this is the coordinate origin, and then you're going to define direction of y, which is in the direction. Doesn't seem like that, huh? Okay. So this is the direction y. This is the direction of the plane surface. And then obviously this is the x direction. So this is x. This is y. Okay. However, I also want to see the cross section here, so I'm going to define. Okay, let's see. I'm going to define a coordinate system. Again, this is y coordinate system. Coordinate system which is rotated 90 degrees, just like similar to the previous example program. So you are going to show you the coordinate system which is rotated 90 degrees, which is this. This is x. So originally this is x, but this is rotated 90 degrees. And then this is y. This is the same location, coordinate origin O. And then you can see cross-section area under the water, which is this. So this is your area of your interest. This is the entire surface of the plane surface submerged under the water. This is, keep that in mind, I took 1 meter length. So this is 1 meter. You're looking at this cross section rotated 90 degrees. So this 1 meter, this is 1 meter. And what is this, by the way? This is not equal to 4 meters. Remember, this is the vertical depth. This is not the vertical depth. This is the y direction distance. This one is 4 meters divided by sine theta. Oh, what is theta? Theta is something you have to figure out, which is, this is theta, which is in essence, this is theta also. Okay? So let me redraw this picture once again. This is a concrete block. Unit width. So this is unit width 1 meter. So I want to find out theta here. The best way to do is, let's imagine this triangle. Since we know this is 2 meters, this is 6 meters. This is 2 meters, this is 6 meters. So this is, we know this is what? This is 4 meters, right? Okay. Then we do know this is 5 meters. Okay. This is 2 meters, this is 6 meters. So the angle theta here can be found by taking tangent. Okay. So this is going to be inverse tangent of theta. Theta equal to inverse tangent of 5 meters over 4 meters out of this triangle. So this is going to give you the angle 51.3 degrees. Oh, that's what we know. So we now know theta is 51.3 degrees. This is an important first step of your solution. Okay, good. And then, of course, out of this cross section, you have a centroid here. Centroid is a geometric center. So this is the centroid of your cross section. Okay. Then you do know depth to the centroid is half of this value. This is 8c, 2 meters. Okay. Now obviously, center of pressure is a little bit below CP, which is CP right here. And that's where the hydrostatic resultant force is going to act through it. That's the center of pressure. F4. So this is a location where hydrostatic resultant force is going to act through it. That's center of pressure, which is a little bit below central. Okay. So let me draw one more figure, which is free body diagram. Free body diagram. Okay. Now in this free body diagram, I'm going to show you only cross section, which is concrete block. It looks like this. So I'm going to identify all the forces acting on this free body diagram right now. So let's see. This is the center of pressure. Then you are going to develop hydrostatic resultant force acting through the center of pressure. Direction is perpendicular to the surface. Then we do know this angle theta is 51.3 degrees. Okay. What else do we have? Well, we are going to probably need to identify CG, center of gravity of this concrete, somewhere. Okay. Then through that center of gravity, you have a weight of concrete, WC. This is how heavy your concrete is. We do know how heavy our concrete is. It is 23.6 kilonewton per cubic meter. So suppose if you find out the volume of this unit width concrete, multiply that volume to gamma, get you weight. So let me see, this weight is gamma times, this is volume. Volume of concrete of a unit width multiplied by the specific weight of concrete gets you the weight of concrete for unit width. So those are the two kind of forces I identified. We have more forces acting on it. If you put this concrete on top of solid foundation, of course the solid foundation is going to get you reaction force. Let's say this is called normal reaction force, N. Normal reaction force is developed. This is the force acting through the centroid of the surface of contact between concrete and solid foundation. And because of this normal reaction force, you're going to also develop force due to friction. Force due to friction is the force trying to prevent this concrete sliding over against this force applied here. So this is a force due to friction. The magnitude of it is going to be determined by static friction coefficient, μs, multiplied by how big your reaction force is. So you have 1, 2, 3, 4 different kind of forces acting on it. Hydrostatic resultant force trying to push the concrete. This is a force due to friction trying to withstand of that force. This is a normal reaction force goes against weight of the concrete. Okay, so we are going to apply equation of equilibrium for those 4 different forces. Equation of equilibrium. Of course, it's a very simple equation. If you sum all the forces in x direction, let's say this is a positive x direction coordinate, must be equal to 0. This is one of the equations. So let's apply this equation to this situation. Okay. First of all, you're going to break this Fr into two component forces. Component of the force in x direction called Frx. Component of the force in y direction, Fry. Okay. And obviously you have an angle theta relationship comes in, so Frx is, of course, Frx is Fr sine theta. Fry is, of course, Fr cosine theta. Okay? So this angle. So this theta is either that angle or that angle. Taking that theta, we can break down this Fr into x and y direction components, sine and cosine. Okay? So let's be careful. So let's sum all the forces in x direction, which is Frx and Ff. Those are the two forces in x direction. So this is going to get you Fr sine 51.3 degrees is equal to Ff, which is mu s times f. So this is one equation you got. Equation 1. How many unknowns do you have? Oh, mu s, this is unknown. This is what we want to know. And this is unknown. Fr, yes, we can determine Fr. This is the magnitude of Fr. We can determine that later, okay? Now, let's do a summation of the force in y direction. Let's say this is a positive y direction, set equal to 0, okay? So you have Fry in negative y direction. This is Wc in negative y direction, n in positive y direction. So this equation tells you n is equal to Wc plus Fy cosine 51.3 degrees. So you come up with the second equation, equation 2. Well, how many unknowns? N is unknown. Wc, we can determine that. Fy, we can determine that. So we have two equations, two unknowns, n and mu s. So you can solve this problem. So first of all, what's Fy? Magnitude of hydrostatic resultant force Fy. Of course, you know this is Pc times A. This is gamma times hc times A. Okay. So let's find out. 9.8 times 10 to 3 Newton per meter cube. This is water's specific weight. Water's specific weight, because that's what the water is creating Fy. Okay. So it's it's probably not a common mistake, but if you want to use gamma of concrete here, it's a totally wrong solution, of course. This is a gamma of liquid creating hydrostatic resultant force. Okay, don't make that kind of mistake. So anyways, hc, what's hc? hc, we know, 2 meters. Okay, so 2 meters. Cross-section area. What is the cross-section area? This is the cross-section area of interest. This is the plane surface submerged under the water, which is 4 meter over sine 51.3 degrees multiplied by 1. Okay. meter over sine 51.3 degrees times 1 meter. So this is area of your interest. So if you punch those numbers in your calculator, you should get 100 times 10 to 3 newtons. Okay, so now we know what FR is. What's WC? Weight of the concrete. Weight of the concrete per unit length. Okay. Weight of the concrete is gamma of the concrete, which is given, multiplied by volume of the concrete. This is gamma of the concrete. Okay, 23.6 times 10 to 3 Newton per meter cube. Volume of the concrete per unit length is, of course, you're going to take a look at this triangle area plus this rectangle area added together, multiplied by 1 meter, gets you the volume. Let's do that. So first of all, 4 meter by 2 meter divided by 2. This is the area of triangle, plus 2 meter times 5 meters. This is area of rectangle. So this is the cross-section area of concrete multiplied by unit length 1 meter. So this is going to be weight of the concrete. So that is 23.6 times 10 to 3 Newton per meter cube times, this happens to be 20 cubic meters. Okay? Anyways. So this is weight of the concrete. If you multiply those two, you get weight of concrete. So, let's take a look at equation 2. From equation 2, you can solve this one for N. N is equal to weight of the concrete, which is 23.6 times 10 to 3 Newton per meter cube times 20 meter cube. That's weight of the concrete. Plus Fr, which is 100 times 10 to 3 Newton cosine 51.3 degrees. This is going to get you amount of normal reaction force in newtons. If you punch those numbers in, you're going to get 534,524 newtons. It's a huge value. Oh. So this is a normal reaction force. Then let's combine this against equation 1. So let's combine this result with equation 1. Equation 1, let's solve this for mu s. Mu s is equal to Fr sine 51.3 degrees divided by N. If you solve this equation for mu s, that's what it is. We do know Fr, we do know N. So let's plug in. This is going to be 100 times 10 to 3 Newton times sine 51.3 degrees divided by N. We got 534,524 Newton. Huge value. This is going to determine static friction coefficient you need. 0.146. Okay, so this is the static friction coefficient required to keep this concrete not sliding against developed hydrostatic resultant force. One thing which is very, very interestingly important here, what is the meaning of quasi-2D analysis? We chose unit lengths of this concrete to determine this value. This is a coefficient, okay? What's the unit? Coefficient doesn't have any unit. It's just a number. That's the beauty of this result. In other words, this is the coefficient. You calculate it based on the unit lengths analysis. This is the coefficient you need for whatever the concrete you have. So if this is a concrete block, in fact, in reality, concrete block is always three-dimensional. Okay? So you actually effectively answer the question saying, suppose if you have a concrete dam which has a cross-section like this with lengths of 100 meters, how much static friction coefficient you need? Well, you need this. This is the answer. Well, suppose you have a concrete block with 10 meter wide with this cross-section. How much static friction coefficient you need? Same, because it's coefficient. That's the beauty of using coefficient together with quasi-two-dimensional analysis. Okay, so you are going to use the 2D analysis to answer the 3D objects problem. Okay. We are going to cover more on this quasi-2D in later, especially at the aerodynamics class, because aerodynamics class we oftentimes use quasi-2D analysis and quasi-2D testing to determine 3D object. Okay? So it's a good idea to start understanding what is the quasi-two-dimensional analysis, what's the benefit, what's the purpose of it. Okay? Alright, that's it.